Understanding long titles. The key here is that I want to understand or develop perhaps methods in which we could better communicate heterogeneity in causal effects in psychology. My field is psychology, but this should apply to other fields as well, using hierarchical models through the brms R package. I used to write Stan code, but now I don't have to. Thanks, Paul. More accurately, this talk should probably be titled How I Learned to Stop Worrying and Love the Samples by Parameters Matrix of Samples from the Posterior Distribution. This is the idea that I want to communicate to my fellow psychologists. How many of you here are psychologists? Woo! How many of you are Finnish? Way more. Okay. This is work that I've conducted or thought through with my colleagues Niall Bolger at Columbia University. He's a professor in the psychology department there. And some of you might know Matt Kay, the developer of such fantastical packages like ggdist, tidybase, and others. And I believe he has attended this convening in the past, but not this year. So psychologists have for a long time recognized that people are different. Yet we've continued to focus as our estimate implicitly on the average causal effect. So we run some experiment, there is a difference between conditions, and we report that difference, yet we then fail to examine whether, for example, this difference might differ between people. And this is what I call heterogeneity. It is the variance between people in causal effects for reasons that are as of yet unknown. Some methods in which this has been addressed before include plotting individual means across conditions. That's a good starting point. A more sophisticated attempt has been made in plotting histograms of person-specific causal effect parameters, so regression coefficients, and then coloring those coefficients, or rather the histograms, on the significance and direction of the parameters. This allows some kind of an overview of how many people have, let's say, positive effects that are significant. There are more sophisticated machine learning kinds of approaches where researchers assess importance for each predictor for each individual and then count what are sort of the important predictors and patterns therein across people. This is sort of the work that we are building on. Bolger, Niall Bolger, my co-author here, wrote a paper in which they directly discussed the multi-level model as a pretty natural source for examining heterogeneity in causal effects. Here's a plot of causal effect parameters for each of about 40 individuals in an experiment. This is a trait valence effect. It's an experimental effect in psychology. Individuals vary, but the distribution of these causal effects in the population has some mean, and the mean has an uncertainty interval, some kind of a confidence interval. What they proposed is that in papers we should report something like the heterogeneity interval in addition to this description of the average effect. The heterogeneity interval here is simply a summary of the distribution of the person's specific effects. So in a multi-level model, it's the mean parameter plus 2 plus and minus the standard deviation of the effect. This approach has been adopted quite widely. There are some heuristics as to what are some interesting cutoffs for heterogeneity to be noteworthy or significant or so forth. But the key thing that's missing here is there's no assessment of uncertainty in the degree of heterogeneity. You just report some point estimates for this heterogeneity interval that summarizes where the population's causal effects are. So what I'm going to describe now is our approach, which to you who probably have done some multi-level models, perhaps of the Bayesian flavor, should not strike at all surprising. So it would be great if while you listen to me, you could think of like, oh, this is why you're dumb, and then during the questions, tell me exactly why I'm dumb, and I will incorporate your feedback in our manuscript that is currently available in preprint format. Our approach is to fit a multi-level model, then choose an appropriate description of heterogeneity. This could be something as simple as the standard deviation of effects in the population, or some more meaningful transformation of parameters in the model. Then instead of just reporting the mean of that, say, standard deviation, you transform the posterior draws into draws of this metric x. And then you visualize. Just as an example, here's some data from a psychological experiment in which multiple individuals, here's person 1, were exposed over several trials to either positive or negative words such as angry or happy, and they were asked to determine whether that word describes themselves. And people on average are faster to say, yes, this word describes me when the word is positive, rather than when it's negative, and people, so they have this sort of a positivity bias. But the question then is, to what extent does this positivity bias vary between people for reasons that are currently unknown? What is the heterogeneity of this valence effect? For example, does everyone show the valence effect? We fit a multi-level model to just simply log transformed reaction times here for simplicity. I know that's not the greatest thing to do, but just ignore that for now. Where we have an intercept and a slope, and those both vary between individuals as described by a multivariate normal distribution. Great, this is very easy now. For me, I'm not a technical person per se. It was a bit of a struggle to try to code this in Stan, but this is how easy it is now, or has been for quite some time. And then you get samples, or I think the nomenclature du jour is now draws from the posterior distribution of the average slope, the average valence effect, and its standard deviation. I then used the distributional package to transform these, on each row to the distribution of the slope. So this is just an R object that represents the distribution. And this calls back to, I think, Richard McElreath's pastiche of the great poet Exhibit, where I heard you like models, so I put models in your models, and now you have a distribution of distributions. And so this, I think, is pragmatically at least very useful to have just the distributions on each row for the transformations that follow. Then once we have fitted the model, or we got the samples, we choose some appropriate transformation of those that describes heterogeneity in a meaningful way for the audience at hand, and also the problem statement. So the key parameters are, of course, the mean and the standard deviation of the distribution in this example of the valence effects. The heterogeneity interval is a very nice sort of location-based summary as to where people's slopes in the population are likely to be. This is a 90% interval, but this is based on the point estimates, the posterior means of the distribution of valence effects. How do we communicate uncertainty in an interval is a question that I don't know a good answer to, but some of you will and will tell me afterwards. Another reasonable summary is the estimate of the prevalence of the effect. So here, the majority of individuals show a negative effect. They respond faster to positive words. They have a positivity bias. We then want to quantify what is our estimate in the proportion of people in the population who have a positivity bias of whatever magnitude, just denoted here as P negative. Too many P's, I'm sorry. Some of you might have heard about this John Krushke's rope approach to inference, the region of practical equivalence. He suggests using it for inference as to what counts as 0 in estimation. I'm not sure if I'm fully sold on that idea, but we can use the same idea here, but instead of inferring something about the population parameter, we're using some interval that is defined by theory to look at the proportion of individuals in the population whose causal effect fall in some meaningful interval. Okay, so now that on each row of the posterior samples we have the distribution, we can use functions of the distributional package or whatever you want to transform the distribution on each row to these metrics. So we have samples of the heterogeneity interval. I'm showing you sort of a visual summary of how this could be represented. You all know how to calculate quantiles and whatnot, but how would you then report this in manuscripts? Not you, my fellow psychologists, maybe Paul, or there was somebody else who is a psychologist. We favor this form of visual representation because it's sort of easier to visually show the posterior uncertainty in this curve versus the probability density function. It gets messy when you start trying to do it over there. And then you essentially, with the heterogeneity interval, have two quantities of interest. You have the lower bound. What is the 5th% bound of the population? That's a very clunky way of saying it. You have the central 90% of the population's causal effects. What is the lower bound of that? Somewhere here. What is the upper bound? It's somewhere here. This is kind of difficult to summarize in one number. At least I couldn't figure, like, what's the summary of an interval where there has to be two. So that's one reason why we favor this kind of a prevalence metric. This loses all information about the magnitude of the causal effect, but psychological theories often don't deal in exact predictions of exact magnitude, so sometimes we're happy with a sort of a negative positive what's going on situation. And visually, again, this is just calculated by fixing a point on the x-axis of the cumulative function and then looking at what's on the y-axis. And you can do it with the point estimates, as has been done before, because you can ask how many people have a negative effect, and it's very easy to do. Well, it's very easy to do with the posterior samples as well, because you just repeat the calculation for each row from the samples. And this is why I learned to stop worrying and love the S by P matrix, because it makes things very, very easy for somebody like me who doesn't know how to do the mathematical transformations to compute the sampling distributions of the quantities that I'd be interested in. And then visually, again, you could show this by showing, here's a sample of posterior, of lines from the posterior. You fix a point 0 here, because we're looking at all the effects that are below 0. And it comes up with a distribution on the y-axis that ranges from, I don't know, 80% to 99% of individuals having a positivity bias in this experiment. Yeah. Rope is great if you have theory that says something is practically equivalent to 0 if it's in this interval, but I have never seen somebody define a theory specifically enough to have that interval in a way that's like well justified. If you have that, however, you can easily, of course, compute that by subtracting two quantities from each other from the cumulative curve. And then for our paper, I wanted to show these because Matt made these wonderful graphics that should illustrate this computation to our target audience. And really, like, this guy knows how to draw pictures. So, sorry? Oh, yes, so this is, yeah, this is the, reminds one of the famous album cover for sure. Relative heterogeneity, so if you divide the standard deviation by the mean, you can talk about what is sometimes referred to as the coefficient of variation. This is an interesting thing to look at when you're comparing heterogeneity between groups, and I'll show you an example of that. I will skip that. In another experiment, people were asked to try to remember lists of words in two conditions. In a free recall condition, where you were just shown a list of words and then a minute later just recall all the words, or a minute later you were shown little cards that sort of cued your memory. People can remember better in the cued recall condition because you're cued, and so it reminds you and you remember better. Interestingly, authors of this paper, not our paper, we took the data from them, noted that people are a lot more variable in their memory performance in the cued recall condition. Even though people on average perform better, they are also, their abilities are more spread out in that condition. Interestingly, if you calculate this amount of heterogeneity ratio, this coefficient of variation, it's the same across the conditions, which is sort of an equality observed in a lot of areas of psychology. Thank you. And these visualizations that we've sort of described in the preprint really lend themselves nicely to overplot. I mean, drawing figures that show both populations and allow visually comparing them. So here we have the prevalence, not the prevalence in this case, it's proportions of people who have better than chance memory abilities in this experiment. It's much lower for the free recall condition than the cued condition. You can easily compare the limits of the heterogeneity intervals, the slopes, meaning the standard deviations of the distributions, and so forth. So we really think that these visualizations and sort of the metrics converted from those would be really useful for communicating heterogeneity with uncertainty beyond the point estimates. Which movie is this? Ghostbusters. So in Ghostbusters, Bill Murray was working at the parapsychology department of Columbia University, and he was asking the participants to guess the posterior distributions, and they had samples. I wanted to talk about this movie because I love it. Thank you very much.